Okay, Unit 1, Lesson 3, Domain and Range. Okay, so it is important to identify characteristics of functions in order to distinguish them from each other. Two of the characteristics you will study is domain and range. So domain is all possible independent values of x, and range are all resulting dependent y values from the domain. So this kind of tells you where it's all coming from. So for example, you start with having the natural numbers, which are the counting numbers, 1, 2, 3, etc. Whole numbers include the number 0. So 0 is a whole number. When you're dealing with integers, you have negative to positive whole integers. And rational numbers are numbers that you can write as a fraction. And then irrational numbers are non-repeating, non-terminating decimals, so pi, square root 2. So you can't really write those in the way you can as like a rational. And so all of these kinds of numbers are real numbers. So they do not include these imaginary numbers. And on the right over here tells you what each part means to help you write the domain and range properly. So here where it says is that you have a number line and you want to practice how to write, let's say, the domain of this shading. So the shading says that, you have to have x values that are less than -2. When you have a non-filled in circle, it means that it does not include that value. And then you have here a single coordinate. So you have a value at x equals 1. And then you have a situation where you have shading from 3 to 5 and not including 5. So in this case, we're going to use the nested notation. So it says, can use the nested notation only if shading is occurring between the numbers. So it's 3 to 5. And so it's x is greater and equal to 3, but less than 5. So this open circle means not include, whereas this shaded in circle means it includes. So the first version has the shaded in the nested notation, whereas the second one says that x is larger and equal to 3 and x is less than 5. Okay, so this will help us write domain and range later. So with this, you have, the smallest number is -3. So from -3 to -2. So y is going to be larger and equal to -3, but it's going to be less than -2. And see how it's not including -2? So there is no underline underneath right over here. So there's no underline over there. Okay. So let's say we look at the other part. So it's a simple -1 to 1. So y is between -1 and 1, and it includes those values. So I needed to draw those underlines to include that it includes those values. And I knew that because you have these filled in circles, which means that there are coordinates there. Okay, this example. Explain why it is improper to record the following. So when approaching this question, what I try to do is I try to draw the situation. This basically says that x is larger than 6, not including, and x is less than and not includes and doesn't include -2. So if I was to draw it, it's gonna be a situation where the -2 and 6 is written, and the shading in never really is in between -2 and 6. They're like separate situations. So when I'm writing this, I do not want to write it in the nested notation. It's not like I have shading between the numbers. So I want to write it separately and say, okay, well, x is less than -2, or an x is larger than 6. I have two different scenarios, and it's not a consistent, it's not a situation where x is, let's say, between -2 to 6. It's the arrows are facing the other way. All right, that's number 4. So for any of these, question 5, so it says to indicate whether it's a function or not, and then write the domain and range. Okay, main ideas. Let's see. So not a function. Graph A and D are not a function because it does not pass the vertical line test, which was something you need to remember from Unit 1, Lesson 1. So if you notice, if I draw a vertical line, I'm noticing that it hits the graph more than once. Therefore, it is not a function. And so writing the domain. So I noticed that the domain of this part A is going to be from -2 to 1 because I have values here, -2. There is a coordinate there, so I'm going to include that value. And the 1 is the highest x value. And so it's simply going to be from -2 to 1. When I look at the range, I notice that there's an open circle, and then it goes all the way up to filled in 5. So how I'm going to write the range is -3. So y is bigger than -3, and less than includes the 5. Okay, so this is how I'm going to write the range. And in this case, I do not include the -3 because there's a there's an open circle at -3 for the range. And there's no like other spots where it's filled in. Okay. So part B. So I have a domain from -5 to 2, and it does not include 2 because there's an open hole at 2. Range. It's from -2 to 3. The lowest value is a -2, and the highest value is a 3. All right. Part C. It's a parabola. It's any polynomial is going to be an x elements of reals. So polynomial meaning terms with positive exponents on the, let's say, the x value. And then the range, y is going to be larger and equal to -3 because the vertex is at 0, -3. Part D, it's equation of a circle. Radius is 3, and so domain is from -3 to 3, and range is from -3 to 3. See how it's continuous? So I'm going to be able to write it as a nested notation. Question E. So this is a rational example. There are asymptotes, and asymptotes a line that a curve approaches as the graph approaches infinity. So these dotted lines help us visualize where the asymptotes are. The filled in parts is the actual graph. So what we notice is that the graph, it exists everywhere, so all real numbers except at x equals 2. There's a vertical asymptote at x equals 2. Okay, we know it's a vertical asymptote because it runs vertically, and the curves approach this asymptote, but not quite touches it. And then for the range, I notice that there's a horizontal asymptote at y equals 3. And so that's why when we write down what the domain and range is, I'm not going to include the x equals 2 and y equals 3. So I'm going to show you, I write that by writing x can't equal to 2 and y can't equal to 3. So, all right. So domain can be found without graphing. So what you're thinking is algebraically, so these are above were all situations when you have the graph. And so you want to think of what are the situations where algebraically you get an error on your calculator. So when we think about that, there's two scenarios, and one is you can't square root a negative. So if you try to take a square root of -2, it'll give you an error. So what we can conclude is that the radicand must be larger and equal to 0. It is okay to take square root of 0. You'll get 0. So we're going to say this, you're going to solve for the radicand when the radicand is larger and equal to 0. So the radicand is the only parts under the root. Meanwhile, you can't divide by 0. So that's why we're trying to solve for when the denominator can't equal to 0. So we find out when that is. Okay, and those are where the asymptotes are. So for question A, okay, we notice that there's a denominator. There is no square root. And I need to find out when that denominator can't equal to 0. Well, I really need to find out when it really equals 0. And so I'm going to set that up. I'm going to factor it. So two numbers I multiply 2 add to 3 is 1 and 2. So my factors are x plus 1 equals x plus 1 times x plus 2 can equal to 0. So when x is equal to -1 and when x is equal to -2, this expression is going to be equal to 0. And remember, we can't have that graph equal to 0, and that's why we want to solve for when it is not equal to 0. And so we're going to write the domain as, x is going to exist everywhere except at x equals -1 and x equals -2, and therefore we write it as x can't equal to -1 and x can't equal to -2. That's part A. Part B, we notice that there's a square root. Square root, we notice we can't take a square root of a negative number, but there's an expression inside, right? And so what you're going to do is you're going to copy and paste whatever is under that square root, and you're going to make that larger and equal to 0. That way you know where the graph actually exists. So when you rearrange, you'll get p is larger and equal to 1. So basically the graph will exist everywhere, when p is larger and equal to 1. But as soon as you put a number like 0, well, you'll get 0 minus 1, and you can't take a square root of -1. So you don't have a graph there. Okay, very similar idea for E. B, it's a polynomial. There's no denominator. There's no square roots. So you just have x elements of reals. Okay, part D, there's a denominator. So you're going to make sure that you say denominator can't equal to 0. You're going to factor it all out. So you take b out as the greatest common factor. You notice it's b squared minus 4, which is an example of difference of squares. 2 times -2 equals -4. Meanwhile, 2 plus -2 equals 0, which is the middle term, I suppose. And so you have b plus 2 and b minus 2 as the factors of b2 minus 4. And so when will that equation equal 0? Well, at 0 and 2 and -2. So we're going to say that domain exists everywhere except at 0 and at 2 and -2. Last one, radicand. There's a radicand, so a square root going on, and there's a denominator going on. So first thing I might write is, okay, x minus 4 has to be larger and equal to 0 to satisfy the radicand scenario. But notice I didn't put the equal sign when I wrote it down. I had to erase that because the denominator can't equal to 0 as well, because I can't have 0 as a denominator. So when you have both in effect, this is what I end up writing, the expression larger than 0. So not equal to, because the radicand is also the denominator. And so you just rearrange and you'll get domain is equal to x elements are real such that x is larger than 4.